Usually when we think about a car, we picture this very specific, deeply ingrained mechanical relationship.
Right, like a heavy metal box with rubber wheels.
Yeah, exactly. And those wheels are physically connected to this, massive engine by an incredibly complex system of like spinning metal shafts and interlocking gears and
This
axles.
is the design language we've been using for, gosh, well over a century now.
Right. You push a pedal, fuel explodes, or battery discharges, and a gear turns a long steel shaft. And then that shaft physically forces the wheel to turn.
It's just this unbroken chain of physical force. I mean,
Mm.
every single vehicle most of us have ever ridden in relies on that exact fundamental chain.
And it feels familiar, right? It's what we know. But what if reinventing the wheel meant physically severing those mechanical connections entirely?
Completely getting rid of them.
Yeah. So, welcome to another deep dive. Today, we're looking at a stack of advanced technical blueprints, engineering schematics, and performance simulations, all detailing this truly wild piece of technology called the JSUN Halbach One.
And we are focusing specifically on the primary propulsion system detailed in these sources because, well, it completely redefined how a vehicle actually moves through the world.
Right. Our mission today is to completely decode this JSUN Halbach Axial Flux motor system. We're talking about a self-contained modular unit sitting directly inside the vehicle's wheels.
Which is crazy on its own.
It is, and as you'll see from these documents, this thing doesn't just propel the car, it physically levitates it, it charges it on the fly, and it solves some of the most frustrating energy bottlenecks in modern EV engineering.
It really does. It forces complete rethink of what a motor is actually supposed to be.
Yeah, I mean, I promise you, while the engineering here gets a bit dense, the real world implications of what this machine is doing are just absolutely mind blowing.
For a long time, motors have just been the dumb muscle of a machine.
Yeah.
But this system treats the motor as a dynamic, interactive component of the whole ecosystem.
Okay, so let's unpack this. To understand how this car does the impossible, we first have to look at the physical shape of the motor itself, right?
Right, the actual geometry.
Yeah, because when most of us picture an electric motor, we picture a spinning cylinder tucked inside another stationary tube. You apply power, and the inner cylinder spins.
The documents refer to that as a traditional radial flux motor.
Exactly. But this JSUN system uses an axial flux topology. I like to think of the physical difference kind of like this. The old motors are shaped like rolling pins spinning inside a pipe.
Okay, sure.
But this new axial flux motor is shaped like pancakes stacked next to each other, spinning face to face.
That pancake visual is actually incredibly helpful for grasping the geometry here. In a traditional radial motor, the rolling pin, the magnetic flux, travels outwards.
And the magnetic flux is the invisible force that actually pushes and pulls to create rotation, right?
Exactly, yes. So it moves radially from the center shaft out toward the edge of the cylinder.
Mm.
But in an axial flux design, you're directing that magnetic flux completely parallel to the axis of the motor.
I want to pause right there for a second because the blueprints mention the stator and the rotor interacting in this pancake setup. For anyone, not building EVs in their garage, what is actually spinning here and what's sitting still?
Okay, so think of three pancakes stacked together. The middle pancake is the stator. It's completely stationary, securely mounted to the car suspension, and it is just packed with electrical coils.
Okay. Middle is stationary.
Right. Then the outer two pancakes are the rotors. They're attached to the wheel itself, and they're packed with permanent magnets. So when you pulse electricity through that stationary middle stator, it creates a magnetic field that grabs onto the magnets in the outer rotors, basically dragging them around in a circle.
Oh, I see.
And because they're spinning face-to-face like that, you are maximizing the surface area of that magnetic interaction in a much thinner, much more compact space.
But the blueprints say JSUN takes this a step further with something called a double-sided Halbach Array. Now, a Halbach Array isn't a new chemical element, right? It's a geometry thing.
Yeah, it's a very specific, mathematically optimized arrangement of permanent magnets.
Mm-hmm.
Normally, a magnet throws its magnetic field out equally in all directions.
Right.
But a Halbach array places individual magnets next to each other at very specific rotating angles. By forcing these magnetic fields to interact in such close proximity, they physically crash into each other and cancel out on one side of the array.
Wait, they cancel out?
Yep, they cancel out on the backside while combining their strength to massively amplify the field on the other side.
So they're essentially folding the magnetic field back in on itself to like double the punch where they need it and completely turn it off where they don't.
Exactly. You are harnessing what would otherwise be wasted magnetic energy. They place these arrays on the spinning rotors so that all the magnetic force is blasted directly into the central stator to create maximum rotational force.
And virtually zero magnetic field leaks out the back toward the wheel or the street, right?
Right. And the performance metrics this arrangement creates are just staggering. I mean, the JSUN system puts one of these independent motors in all four wheels, each delivering 150 kilowatts of power.
That's 600 kilowatts total, which firmly translates to hypercar territory.
Absolutely.
Like the performance simulations show a 0 to 60 miles per hour acceleration in 1.8 seconds and a top speed of 420 kilometers per hour.
Which is insane. But the defining metric for engineers is the peak torque density, which here sits at 24.8 to 30 newton meters per kilogram.
That sounds high.
It's very high. Some of the bench tests in the documentation are even exceeding 30. That's what allows these incredibly light motors to deliver maximum torque instantly at literally any speed.
But the headline number we really need to focus on is the efficiency, right?
Oh, definitely. They do all of this while maintaining a peak efficiency of over 97%.
Which is unheard of. And even maintaining highway speeds of like 120 kilometers per hour, the motor stays above 94% efficiency.
Yeah, barely drops.
Now, I have to push back here for a second. Sure, hypercar acceleration and 97% efficiency sound great in the lab simulation, but physics always collects its tax.
That is very true.
Massive power output usually equals massive energy waste through heat and friction. How is this system actually beating the brutal physics of energy drain that plague, pretty much every other EV on the road?
Well, it doesn't beat physics, right? It systematically outsmarts the traditional friction points using advanced material science.
Oh.
Let's break down how it targets and kills energy waste piece by piece.
Okay, let's do it.
So the first major drain in any electric motor is cogging torque.
Cogging torque. I've read about this in the sources, but what is actually happening physically when that occurs?
Have you ever manually spun a small electric motor, maybe on a toy or a drill, and felt a sort of bumpy resistance, like it wants to constantly click into place as you turn it?
Yes, exactly. It feels jagged, not perfectly smooth at all.
Right. That is magnetic notching. The magnets in the rotor are constantly trying to lock onto the steel teeth in the stator. Every time it locks and unlocks, it creates a tiny bit of mechanical resistance.
Ah, I see.
But that Halbach Array flux cancellation we discussed earlier, it smooths out that magnetic field perfectly. The JSUN system reduces that bumpy cogging torque by 30 to 40%.
Wow. So you aren't just saving the energy previously wasted fighting those magnetic bumps, you're probably improving the ride quality too, right?
Oh, massively. You're improving the noise and vibration harshness inside the cabin by roughly 40%. The ride just becomes impossibly smooth.
Okay, so that's cogging torque. What's the next drain?
The next major drain is eddy currents.
I've heard the term eddy currents thrown around in electrical engineering, but what is an electrical current doing inside a solid piece of metal?
Think of it like an electrical current that gets confused. As the intense magnetic fields spin around the metal stator at thousands of times a minute, they induce these tiny unwanted loops of electricity inside the solid metal itself. Yeah, these little loops of current just spin in place, creating their own opposing magnetic fields that actually fight the motor's rotation. And they generate a ton of waste heat in the process.
Oh, wow. So it's literally fighting the motor's own momentum, like swirling eddies in a river, catching a boat and dragging it backward.
That is a perfect analogy. That parasitic drag is a massive source of wasted battery power. To stop it, JQ doesn't use standard steel for their stator. They use graphene-reinforced steel laminates.
Graphene again?
Always graphene with these guys. Graphene acts as an atomic-level barrier that fundamentally changes the electrical resistance of the steel. It's effectively building microscopic walls that break up those parasitic electrical swirls.
And that single material change minimizes eddy current losses by 25%.
Exactly. 25% just gone.
Wow, okay. So we've smoothed out the magnetic bumps, we've built walls to stop the parasitic electric swirls inside the metal. What is the next energy drain on the hit list?
Hysteresis. This is the energy lost when the magnetic field within the steel reverses direction over and over again. You can sort of think of it as magnetic memory resistance.
Magnetic memory resistance, how does that work?
Well, the atoms in the metal have to physically flip their magnetic orientation every time the rotor passes. Flipping them takes a little bit of energy. By optimizing the rotor steel and using those Halbach arrays to precisely shape the magnetic flux, they reduce hysteresis by 15%.
Okay, so they're just chipping away at all these invisible losses.
Right. And finally, the most obvious drain of all, mechanical friction. Because this is a direct drive architecture, meaning the motor is sitting right inside the wheel hub itself, there's absolutely no gearbox.
Oh, right. If the motor is the wheel, you don't need a transmission.
Exactly.
No gears grinding together, no heavy drive shaft spinning under the car, no universal joints bleeding kinetic energy.
You eliminate thousands of pounds of moving parts and all the friction they generate. When you combine the reduction in cogging torque, eddy currents, hysteresis, and mechanical friction, you end up with an overall energy consumption reduction of 30 to 50% compared to a conventional electric vehicle.
That is just wild to think about. But reading through these schematics brings up a huge physical, kind of logistical question for me.
Okay, what's that?
Well, eliminating electrical waste is one thing, but how does the physical hardware actually survive the environment? Like, the specs say these outer rotors can spin at up to 50,000 RPM.
Yeah, 50,000.
That's 50,000 revolutions per minute. That is like putting the rotational force of a high-end jet turbine inside a wheel hub that is, bouncing over potholes and speed bumps. How does it not just fly apart from the sheer centrifugal force?
This is where the electromagnetic design leans entirely on advanced material science again. The centrifugal force tearing outward at 50,000 RPM is immense. I mean, standard metals would warp, stretch, and eventually shatter,
Huh.
completely destroying the car. But that graphene-reinforced steel we mentioned earlier doesn't just block electrical currents. Graphene is, at a molecular level, one of the strongest materials ever discovered.
So it's pulling double duty.
Exactly. Incorporating it into the steel matrix provides the immense mechanical tensile strength required to physically hold the rotor together under that insane kinetic stress.
Okay, so the wheel won't explode on the highway. That's good. But what about the heat? You push 150 kilowatts of electricity through a compact pancake motor, and you are going to generate a literal firestorm of thermal energy.
And heat is the absolute enemy of electrical efficiency. As heat goes up, electrical resistance goes up and you lose power. Standard high-performance EV motors use heavy copper or aluminum heat sinks to try and, draw that heat away.
Right, big heavy metal fins.
Yeah, but the JSUN motor uses upcycled graphene composite heat spreaders.
Okay, so how much better is a graphene heat spreader than standard copper? Are we talking a small incremental bump here?
Oh no. It is a totally different paradigm of thermal management. Copper has a thermal conductivity of about 400 watts per meter Kelvin. These graphene heat spreaders have a thermal conductivity of approximately 4,000 watts per meter Kelvin.
Wait, 4,000?
Yes. They pull heat out of the sensitive electrical components literally 10 times faster than copper. And they pair this passive graphene cooling with active, AI-controlled microfluidic channels built directly into the metal of the rotor and stator.
So the central computer is dynamically pumping coolant through, like, microscopic veins in the metal based on how hard you're pushing the car?
Yeah. The AI predicts load demands milliseconds in advance and adjusts the fluid flow in real time. Because of this combination of liquid cooling and graphene heat spreaders, even when you're redlining the motor on a track, the maximum hotspots inside the hardware stay below 85 degrees Celsius.
Wait, 85 degrees Celsius? That's just a hot cup of coffee.
Yeah.
You could practically rest your bare hand on the motor right after a drag race.
It is a bizarrely cool operating temperature for a high-output motor, and it keeps residual thermal power loss to less than 5%. They even wrap the entire motor housing in a graphene-reinforced polymer shell, which drastically cuts the unsprung weight of the wheel while helping to conduct that final bit of heat out into the passing air.
Here's where it gets really interesting, though. We've established these motors are manipulating massive magnetic fields with surgical precision to drive the wheels without melting, right?
Right.
But as I read further into the design documents, JSUN realized that since they already have these incredibly powerful, highly controlled magnetic fields sitting at the four corners of the car, they could use them for things completely unrelated to just spinning the wheel.
Yes, this is my favorite part.
And the solutions they came up with sound like pure science fiction. The wheels are also levitation devices.
What's fascinating here is that the motor stops being just a propulsion tool and becomes an active physical interface with the infrastructure of the city itself. The documents outline true Maglev capability.
Maglev, like the bullet trains.
Exactly like the trains. Those same in-wheel Halbach arrays we discussed earlier, the ones focusing power into the stator, they can also dynamically focus magnetic flux downwards, directly toward the surface of the road.
But they can't just push against regular asphalt, right? They need a specific magnetic surface to push off of, don't they?
Right, they do. When the vehicle merges onto a specialized Maglev-enabled lane on a highway, the arrays in the car's wheels synchronize with passive magnets embedded in the road surface. This interaction generates a massive repulsive lift force of 1,500 to 2,500 newtons per wheel.
So it physically pushes the entire 2-ton car up off the ground.
It lifts the entire chassis, creating a 10 to 20 millimeter levitation gap. The central AI manages this gap continuously, providing active feedback to the wheel motors to maintain stability to within plus or minus 1 millimeter.
Wow.
Yeah, instantly adjusting if a crosswind hits the car or if the road dips.
I mean, the efficiency gain from that has to be astronomical. If the tires aren't touching the road, you aren't fighting the road.
By breaking physical contact, the system reduces rolling friction by roughly 80%.
That's insane.
But the infrastructure interaction doesn't stop at levitation. Those same magnetic arrays facilitate dynamic wireless charging, or DWC.
Right. Charging the battery while actually driving at highway speeds. I saw the term resonant coils in the blueprints regarding this. How does power actually cross an air gap between the road and the car without just dissipating into the environment?
It relies on magnetic resonance. The road has embedded coils of wire, and the car has corresponding coils. If you tune both sets of coils to vibrate or resonate at the exact same electromagnetic frequency, energy can transfer between them highly efficiently, completely ignoring the air gap.
Oh, that's brilliant.
The car's Halbach arrays focus their magnetic flux toward these road coils, logging onto that resonant frequency and increasing the energy transfer efficiency to over 93% while moving. The car can pull in up to 300 kilowatts of continuous power while cruising.
I want to touch on one more thing the AI is doing with these 4 independent wheels because it fundamentally changes how the car handles. Torque vectoring.
Right. Because there is no central engine or axle connecting the wheels, the central AI manages all 4 corners individually.
So it's basically 4 different cars acting as one.
Basically, yeah. It can instantly push power to the outside wheels while slightly dragging the inside wheels during a turn. This active torque vectoring complements the maglev lift and drastically improves cornering stability. The simulations show it increases lateral grip by more than 15% during high-speed maneuvers. It is calculating traction slip millisecond by millisecond.
So what does this all mean for you, the driver? If you're taking this car on a long road trip, how does a 97% efficient, floating, self-cooling, hyper-intelligent motor actually impact the battery pack you are relying on to get to your destination?
This is where the JSUN ecosystem completely changes the calculus of electric vehicles. Because of all this compound efficiency, killing eddy currents, cutting mechanical friction, levitating over the road, the vehicle only consumes 0.08 kilowatt hours of battery energy per kilometer.
Let's put that in context really quick. A standard electric SUV on the road today consumes around 0.15 to 0.20 kilowatt hours per kilometer.
Exactly. So the JSUN Halbach 1 is using less than half the energy of a conventional EV to travel the exact same distance. And because the energy requirement is so drastically reduced, the total size of the battery you need to carry drops by 30 to 40%.
Which means you don't need to cram thousands of pounds of highly volatile, incredibly expensive liquid lithium-ion batteries into the floorboards just to combat the vehicle's own mechanical inefficiency.
Right. And this extreme vehicle efficiency bridges the gap to make sodium-ion or NaN-ion solid-state batteries viable.
Sodium instead of lithium.
Yes. Historically, sodium-ion chemistries have been penalized for having a lower energy density than lithium. They're heavier for the amount of power they hold. Furthermore, JSUN uses solid-state architecture, meaning they replace the flammable liquid electrolyte inside the battery with a stable, solid material. This makes them incredibly safe, but traditionally even denser and heavier.
But when your car uses half the energy to move, that density penalty basically just vanishes.
The math flips entirely. JSUN can utilize these heavy, lower-density, highly stable NaN-ion solid-state packs, and they still deliver a standard cycle range of over 1,200 kilometers on a single charge.
1,200 kilometers without needing lithium. That's huge.
Yeah.
And if you happen to be driving on one of those dynamic wireless charging highways we discussed earlier,
Then you achieve infinite range operation.
infinite range.
Yeah. The vehicle consumes about 8 kilowatt hours per 100 kilometers, but those resonant road coils can deliver 120 to 150 kilowatt hours over that same distance. You are pulling in far more energy from the infrastructure than the motor is consuming to propel the car.
That completely eliminates range anxiety. And we haven't even talked about stopping the car yet. If the wheel motors are doing all the pushing, are they doing all the pulling too? The schematics mention 100% regenerative braking.
Yes. The vehicle features 0 mechanical brake pads, No metal calipers squeezing a heavy steel rotor.
Oh,
No brake fluid at all.
wait, absolutely zero mechanical pads. If I slam my foot on the brake pedal at 100 miles an hour, what is physically stopping a 2-ton vehicle?
All deceleration is handled electromagnetically. When you press the brake pedal, the system reverses the electrical flow. The spinning wheels now physically turn the rotors inside the motor. The motors instantly stop acting as propulsion devices and switch to acting as high-efficiency electrical generators.
Oh, I see.
The kinetic energy of the speeding car is converted directly into massive amounts of electrical resistance, which stops the wheels, while simultaneously blasting that raw electricity straight back into the sodium-ion battery matrix.
That's a massive closed energy loop.
Yeah. During urban driving with lots of stop-and-go traffic, this continuous loop returns up to 45% of the vehicle's kinetic energy straight back to the battery.
And from a basic ownership and maintenance perspective, if you have no brake pads, you have no brake wear.
Zero wear.
No squeaking, no replacing worked rotors, and zero brake dust, which is actually a surprisingly huge source of heavy metal air pollution in major cities.
The lack of physical wear across the entire vehicle brings us to the ultimate design philosophy outlined in the JSUN blueprints.
Right, because if there are no brake pads to wear out, no gears grinding together, and the motor runs perfectly cool at a mild 85 degrees, what actually happens when it finally reaches the end of its life? We are so accustomed to everyday appliances, cars, and motors just being treated as disposable. A bearing goes out and you throw the whole thing in a landfill. How does the system fight planned obsolescence?
If we connect this to the bigger picture, JSUN has designed this entire architecture for what they call an infinite life cycle. First, the operational lifespan of the motor itself is projected at over 1 million cycles.
1 million cycles.
Because there is virtually no friction and heat is so tightly controlled, you're looking at less than 1% degradation in torque outcome over a decade of heavy use.
But eventually, over decades, something has to give. A rock hits it, a seal breaks.
The modular design accounts for that. If a single in-wheel motor module eventually suffers a critical failure, you don't scrap the car. The self-contained pancake unit unbolts, and a new one can be swapped onto the chassis in less than 2 hours.
That's incredibly fast.
But it's what happens to that broken, discarded motor that represents a true leap in industrial circularity.
This is where the research gets into circular manufacturing. I assume they don't just melt the broken motor down in a foundry, right?
No, because standard melting or shredding heavily degrades materials. You mix impurities in, and the recycled metal is always lower quality than the original. JSUN bypasses this by using a proprietary process called plasma catalytic upcycling.
Okay, plasma catalytic upcycling. How does that actually work without destroying the base materials?
It is brilliant chemistry. They take the end-of-life motor laminates, the carbon fiber chassis parts, and the shredded remains of dead battery packs. They place all of this mixed waste in a sealed chamber filled with argon and hydrogen gas. Then, they blast the chamber with standard industrial microwaves.
Wait, literally microwaves, like the technology in a kitchen appliance.
Using the exact same frequency, 2.45 gigahertz.
Yeah.
These intense microwaves interact with the gases to create a non-thermal or cold plasma field. This is a bizarre state of matter where the loose electrons get incredibly hot, around 10,000 Kelvin, but the heavy bulk gas around them stays near room temperature.
So you have these microscopic pockets of insane heat ripping things apart at a molecular level, but you aren't actually burning or melting the physical chunks of material.
Exactly. The cold plasma efficiently breaks the strong carbon bonds in the waste materials without causing broad thermal degradation. But here's the genius part. They introduce nickel and manganese nanoparticles, which they retrieve from those old, dead sodium batteries, into the plasma field to act as chemical catalysts. These catalysts essentially act as chemical guides, drastically lowering the energy needed for the free-floating carbon atoms to reorganize themselves.
So the carbon from the broken motor is floating in this plasma. What do the catalysts guide it to reorganize into?
Into high-purity, defect-free monolayer graphene.
Wait, really?
Yes, they literally take the mixed carbon waste from the broken motor and dead batteries, reorganize its atomic lattice structure within the plasma field, and turn it into the pristine, ultra-strong graphene that is then built right back into the heat spreaders and steel laminates of the next generation of motors.
So the degraded waste of the old car becomes the premium raw material for the new car. It's a completely closed loop.
The process is so efficient that it consumes roughly 60% less energy than conventional graphene production. Because they're using their own waste as the raw feedstock and running low-energy microwave plasma, the entire JSUN ecosystem is projected to achieve net negative life cycle CO2 emissions within 3 years of operation.
So to bring this all together for you listening, the JSUN Halbach motor isn't just a fancy way to make a rubber wheel spin faster. By rethinking the very geometry of magnetic flux and obsessing over the material science of literally every friction point, they've built a frictionless, self-cooling, energy-generating, levitating marvel of circular engineering.
It really is a marvel.
This single piece of hardware bridges the gap for heavy sodium-ion batteries, eliminates mechanical wear entirely, and physically upcycles its own waste into miracle materials.
It's a complete paradigm shift in how we approach physical layer engineering, honestly, proving that incredible performance and deep sustainability do not have to be mutually exclusive.
It really is. And it leaves me with one final thought for you to chew on today. If this level of ultra-high efficiency, modular axial flux technology can be perfected to hurl a 2-ton car down the highway at hypercar speeds,
Hmm.
imagine what happens when this exact same motor architecture scales down.
Oh, for sure.
What happens when these infinite life cycle, self-cooling, highly efficient motors are used to power the delivery drones dropping packages on our porches, or the heavy HVAC systems cooling our office buildings, or the washing machines in our homes? If the motors of tomorrow never degrade, perfectly harvest their own energy, and their materials perfectly upcycle into stronger versions of themselves, we aren't just changing how we drive on the highway. We are fundamentally ending the era of the disposable machine.
This raises an incredibly exciting question about how quickly the rest of our global manufacturing infrastructure can adapt to support this new physical reality.
That's a question for another day. Thanks for joining us on this deep dive.